Hello, students, and welcome to today's lecture where we are going to go over acid-base equilibrium and specifically some of the functions of acid-base equilibrium that have terms that we're going to want to memorize here. So what we have to begin with is that we actually have a image on the screen that ends up showing a typical kind of acid-base equilibrium where we have something like hydrochloric acid. It's hitting water, and it ends up making a hydronium, a H3O plus. Okay, and then we also get the conjugate of it right here. And the idea here is that when we put acids in water, the acid is both attaching to the water molecule itself, but it's also going backwards from the water molecule and attaching to the acid. Okay? And when we're thinking about this in acid-base equilibrium, what we're really thinking about, okay, what is the concentration of this, and the strength of our acid is going to depend on what the concentration of this right here is. So whether the left to right hand reaction, the forward reaction is stronger, or if the reverse reaction is stronger, is going to determine the strength of our acids here. Okay. But the first thing that we're going to want to do is go ahead and talk about the conjugate acids and bases. Okay. So a reminder that every acid is going to have a conjugate base that kind of pairs with it, especially in a equilibrium reaction like this. So for instance, this right here is the acid in our case for this reaction, because this is something that's going to give off a hydrogen. So anything that can give off a hydrogen is going to be an acid. And it's always going to have a conjugate base, which is going to have the leftover things that can absorb a hydrogen. So this one loses hydrogen. This is its partner, its conjugate base, that gains a hydrogen. So this is the conjugate acid to this conjugate base, and this one is the conjugate base to this acid. Okay. The same goes for our water molecule. Our water molecule, this water molecule is the base because it can absorb a hydrogen, and this one is the acid because it can release one. So these are the conjugate acids and bases to one another. Okay. And that's going to be one of the big terms that we're going to be using in this section. It's something that's definitely going to be tested on in the future. However, it's a fairly easy one. You're going to look and see the main non-acidic part, or the part that's left over once the hydrogen leaves. Okay. This one is an example that uses NH3 and HCl. Okay. And as you can see here, we have NH3, HCl, and we end up making ammonium right here and a chlorine ion. This one would end up being our base. This ends up being the acid. Okay, so this is our first conjugate acid-base pair. This is our second conjugate acid-base pair. This is the acid in this situation because it releases a hydrogen or releases a proton. This is the base. This one is an acid. This is a base. Okay. Water molecules also tend to do this. In this case, we would say, just because this is the one that's listed first, we would say that this is the acid, this is the base because it absorbs a hydrogen, and then this one ends up being an acid. Okay. Two water molecules also do that, which is why water is indicated in our acid-base pH chart. Okay. Next is how we write out a acid equilibrium equation in standard equilibrium terms. And what you'll notice is that this is going to look very similar to the kind of reactions that we had from before, where we have our acid, we have our reactants, and they end up going on the bottom. And then we have our products, and they end up going on the top. And this is how we write out our basic equilibrium constant here. Okay. And so an equilibrium constant for an acid and a base is going to end up being the exact same thing. You'll notice that one thing that we're going to drop off here is we're going to go ahead and drop off the concentration of the water because, well, the concentration of the water is going to be much too high, and it's going to mess with our overall idea with the system here. So what we're going to have is we're going to have this reaction here, and it's going to go to these two right here. And this is how we calculate the Ka for a particular acid or base. Okay. So as an example here, this ends up being acetic acid. And acetic acid is going to go ahead and make H3O plus the base, the conjugate base. Okay, and then we'll have the acetic acid on the bottom. And this will either be H plus or it'll be H3O. Both of them end up being correct. Okay, so this is our basic process for writing out the equilibrium expression for this particular reaction. Okay, and this will go ahead and bring us to our next term, which has to do with a thing that's called disassociation. Okay. And disassociation is going to be a term that's useful for us, and it's essentially stating how well the hydrogen is able to split apart from the acid. Okay. Okay. And we spelled that completely wrong. Okay. And essentially here, the more disassociation that an acid has, the stronger that acid is going to become. Okay, and that should make some pretty keen sense to us right here. The more H plus that we have in a general reaction, the stronger that acid is, because we always measure acids in terms of strength. Okay. So disassociation, the bigger the disassociation, the stronger that the acid is going to become. And in general, when we end up describing acids, we're going to end up describing them as being either strong acids or weak acids based off of how strong that disassociation is. Okay. So in terms of equilibrium, for a strong acid, what we'll notice is that before disassociation, we'll have our acid here, and a majority of the acid is going to disassociate and fall apart. Okay. For a weak acid, we're going to have most of the acid stay together, and only a little bit of it is going to fall apart there. Okay. So this is an example using hydrochloric acid and hydrofluoric acid. In case of hydrochloric acid, it's a very strong acid. It almost completely disassociates in water. And this right here is hydrofluoric acid, which does not disassociate well in water. Okay. There are various ways for us to go ahead and describe the acid strength. So if it has a Ka value, okay, which is the value that we can calculate here, and the Ka value is relatively large, then we usually consider it a strong acid. Okay. We can also describe that as saying that the ionization equilibrium is far to the right. We can also go ahead and compare the concentration of the acid particles to the concentration the concentration of the hydronium ion to the concentration of the acid. And if the concentration of the acid is greater or about equal to the actual acid, it's a strong acid. And the strength of the conjugate base compared to that of water. Okay. And if the conjugate base is really, really strong, or sorry, if the conjugate base is really, really weak, then it's going to be very highly acidic. Okay. Likewise, if Ka is really, really small, we're going to go ahead and say that that's a weak acid. All right. So right here we have an example of a couple of acids. Okay. And what you'll notice here is that we have some acids right here that are 1.2 times 10 to the negative second. Okay. Now in terms of Ka values, that's actually really, really high. This is actually fairly acidic, and this is a fairly strong acid right here. Whereas this number right here, 1.6 times 10 to the negative 10th, that number is really, really small. That's like 0.0000000000016. Okay, so that's a really, really small number. Okay, so in general, if you see a Ka value and it's in like the 2s or the 3 or 10 to the negative 2 or 10 to the negative 3, you're going to think, okay, that's a pretty strong acid there. Okay, and here's some other example here. Okay, here's some chlorous acid, nitrous acid, hydrofluoric acid, which is a weaker acid. Okay, and then these right here, which are hardly acids at all, but just because of what they are here. Okay, next we have relative acid strength here. Okay, and relative acid strength is going to be, this is just a way to go ahead and measure what the conjugate base is. So if you have a strong acid, you're going to have a really weak base. And if you have a strong acid, very weak base. If you have a very weak acid, you're going to have a very strong base. Okay, so these are things that are interrelated to each other, that you're always going to have a balance between a weak base and a strong acid, and a strong base and a weak acid. Okay. This is just another example of the case of figuring out which hydrogen is going to often be acidic. And usually it's going to be not going to be the hydrogens that are on the carbons themselves. More often than not, if you're going to see something that's going to be acidic, it's going to be on a carboxylic acid, or it's going to be attached to a oxygen. Okay, this acidic hydrogen is actually shared between these two oxygens. This is a carboxylic acid molecule with these two oxygens on the end here, and that hydrogen that's on there is going to be the one that's going to be the acidic hydrogen. Okay. And again here, this is another carboxylic acid. Notice that we have these two oxygens right here. This is going to be the acidic hydrogen. So if you're tasked with trying to figure out which hydrogen is going to be coming off with a large carbon molecule like this, you'll always look for the one that's right here with this carboxylic acid group. Okay. The last thing is going to be the pH scale. So a lot of you know that the pH scale is essentially the negative log of the concentration of hydrogen. Okay, and essentially what we need to know is that the pH scale is going to be fairly similar to Ka, and Ka and the pH scale seem like they're pretty close. They are different. The pH scale is the negative log of the concentration of hydrogen, so it kind of makes sense that they're going to be similar, because as this goes up, the Ka will go up, but they are going to be different. So you do need to make note of that. But in general, we have our pH scale that allows us to kind of evaluate the equilibrium expression at room temperature, and often it is at room temperature. Okay. And this last one, oh, I don't think that we actually need any of that there. All right. That's going to go ahead and close us out for what we actually need for this lesson right here. Again, some of the things that we're really keen on is really identifying the different types of acids and bases, recognizing that the percent dissociation is going to determine the percent dissociation is going to determine whether or not something is a strong or weak acid. And then knowing basically that the larger the Ka, the stronger the acid is. Okay, and these are all considered our weaker acids here. Some of our stronger acids will have even higher Kas. And we'll have a couple of problems that'll end up showing that right here. Being able to identify different conjugate bases is really key. So for instance, this one right here, our conjugate base would end up being, NO2 minus, ClO2 minus, okay? And being able to identify that's going to be a really big one. And then knowing that pH scale and Ka are closely related, but they are not altogether the same. Those are the things that we want to go ahead and remember and be mindful of. And that should be able to close us out for today. And just as a reminder, remember, be lazy.